Okay, so yeah, today, as I announced in the message, and I said here an hour ago, but also this is in our schedule. I'm going to talk about how CaNPAN tools can be used to model the evolution of and multi-zone nucleosynthesis in classical novae. So I start with just showing you a few slides to explain what classical nova stars are. And then I will show you the CaNPAN computational tools that can be used to model nova evolution and nucleosynthesis, okay? So CaNPAN projects, nova introduction, okay? So this is first slide is just a common slide that gives general comments on CaNPAN projects. So therefore, I'm not going to read it. So this is just a common slide. Now, this is a slide related to classical nova stars. Okay. So you probably heard about nova stars. These are stars that suddenly become bright on the night sky. The increase of their brightness is caused by a thermonuclear explosion of hydrogen-rich material on the surface of a white dwarf star. Okay, so therefore, the title to the slides says that nova explosions occur in closed binary systems on white dwarfs accreting hydrogen-rich material from their main sequence, subgiant or red giant companions. Okay, so let's have a look at this picture. Here on the right, in the center on the right, you see a white dwarf. This is a compact object. The final evolutionary stage of low and intermediate mass stars, as I told you about in the slides on the introduction to stellar astrophysics. So these are compact stars with radius approximately equal to the radius of Earth, and they are in hydrostatic equilibrium thanks to the pressure of degenerate electron gas. Okay, if these stars were more massive initially, they would end up as neutron stars or black holes. But given that the initial masses are relatively small, say from approximately 1 solar mass to up to say 8 solar mass, these stars end up the evolution as white dwarfs. If a white dwarf is a single star without a companion, then it will just cool down and will gradually die, will become black dwarf as its temperature goes down. But this takes a very long time, cooling down of white dwarfs, single white dwarfs. But the different story is when a white dwarf is a member of a closed binary system. We call closed binary system systems of stars in which the evolution of a star is substantially different from the evolution of the corresponding single star, which means that the stars in closed systems can interact with each other. They can exchange material, and this is what's happening in classical nova closed binary systems. So you can see here on the left the companion, the secondary star in this closed binary system is main sequence star. And if the distance between white dwarf and its companion is small enough, if the separation between these two stars is short enough, then at some moment the companion, the secondary star, as it evolves, its radius increases, and at some moment, the companion star will fill its row slope. Row slope of a star in a binary system, in a closed binary system, is a region where gravitation by this star dominates, right? But when the radius of the star will reach its row slope radius, we call this the star has filled its row slope. Then the material from the star can almost freely escape. It escapes through this inner Lagrangian point here, where the sum of gravitational force and centrifugal force is actually zero. So therefore material escapes this star from the inner Lagrangian point, and it finds itself in a row slope of a white dwarf here. This is the row slope of the white dwarf. This is row slope of companion. And then this material is attracted by the white dwarf because the system has an orbital rotation. This is shown with this arrow. This is orbital rotation. It rotates here counterclockwise in this plot. Therefore, the material that enters here, which is shown with red arrow, enters into the row slope of a white dwarf. It has angular momentum. Therefore, it doesn't go directly into the surface of the white dwarf. Instead, it creates an accretion disk. This is a common situation in closed binary systems, formation of an accretion disk. Then some processes, not completely known as yet, inside the accretion disk result to loss of angular momentum in the disk. And as a result of the loss of angular momentum, material on the disk migrates towards the surface of the white dwarf, and finally it gets accreted by the white dwarf. So the net result of this interaction closed binary system, that mass of the accreted of the envelope and accreted hydrogen rich, because this is main sequence star, the mass of the hydrogen rich envelope accreted by the white dwarf grows with time. It grows with time, and it gets compressed by relatively strong gravitational field of the white dwarf. And as a result of this, it gets heated up, the material. And eventually, when its temperature at the bottom of the accreted envelope reaches high enough value of 100 million Kelvin, hydrogen burning starts. Hydrogen is ignited, but because thermodynamic conditions at the bottom of the surface of the white dwarf is still close to degenerate conditions, this ignition has a form of thermonuclear explosion or thermonuclear runaway. As a result of this thermonuclear explosion, convection develops in the envelope, the accreted envelope of the white dwarf, and also the accreted envelope begins to expand. And after some relatively short time, it gets ejected from the binary system. Okay, and it is during this process of the expansion of the accreted envelope after thermonuclear explosion that we see the increased brightness of the binary system, and which we call as a classical nova star. Okay, and because after the envelope is ejected after the explosion, the accretion of hydrogen-rich material provided by white dwarf's companion resumes. So therefore, such nova explosions in the same binary system can happen many times. So it can repeat. So therefore, this sentence says a white dwarf that is a part of a semi-detached binary system can undergo repeated explosions. Okay, so this is the main, the basic physics behind nova, classical nova stars thermonuclear explosions. Okay. Okay. So now you, of course, as always, can have a look at these slides, which are made in the form of Jupyter Python notebook. And you can look at the slides in more detail during the week, next week. But you also can execute some cells here. So this is just a Python notebook cell. In this cell, as you can see, I calculate, you can calculate, you can change parameters. So here, first, this cell just takes physical and astronomical constants, first of all. The solar mass in kilograms, the solar radius, solar luminosity, Newton's gravitational constant, and Stefan Boltzmann constant. Okay, but the next cell, Python notebook cell, it calculates, as the comment says, it calculates Rochlop radius of a white dwarf and its companion in solar units and solar radii. So you can try to execute this cell. You can change parameters. For instance, here, for parameters of the binary system, I use 1 solar mass for the white dwarf mass, 1 solar mass of the white dwarf and solar mass, 1.5 solar masses for the mass of its hydrogen companion, main sequence companion. P equal 4 is just the orbital period of the binary of the white dwarf in hours. This is orbital period of white dwarf. Yeah, this orbital period of the binary in hours. So you can see that classical nova binary systems, they actually have relatively short orbital periods for the several hours. So in this case, I use 4 hours. Then this cell calculates some additional parameters. This is just the mass ratio, white dwarf to companion mass, etc. And there is here a link to the paper from where I took this equation that calculates the Rochlop radius. And for these parameters, we find that Rochlop radius of the white dwarf in this case is in solar units 0.596, Rochlop radius of the companion solar radius 0.7, and the mass is 1.5. So this means that the companion definitely fills its Rochlop, because the main sequence star with mass 1.5 definitely has a radius above 0.7 solar radii. Okay. And also this ratio gives the orbital separation of white dwarf and companion. So the semi-major axis actually in solar units, again 1.7 solar radius for this orbital period. So this is a relatively close binary system. So you can change parameters and do these calculations. Okay. Okay. So now a summary of observables that can be used to study nova explosions and nucleosynthesis. So these are actual. Actual means that were already measured, and possible observables. Possible means that they, in principle, we hope will be eventually observed, but have not been observed yet. So therefore, actual and possible observables of nova explosion and nucleosynthesis. So as I already said, suddenly a new, therefore it's called nova, this is Latin for new, star appears in the sky. And this is caused by an increase of white dwarf's luminosity, which goes from approximately 100th of solar luminosity. This is the typical luminosity of white dwarfs, 100th or even lower. And because of the explosion, luminosity of the white dwarf goes from 100th of solar, 10 to the minus 2, to 10 to the 4, 10,000 solar luminosities, which quite significant luminosity. In stellar magnitudes, this change of luminosity corresponds to a difference in 15 magnitudes. Okay, 15 magnitudes. So you know that with the naked eye, we can see on the good night sky stars down to approximately 6 magnitude, 6 magnitude. The higher magnitude means dimmer star. But for instance, if the star had magnitude, say magnitude so 15 magnitudes, this is the difference in magnitudes. If it was below the 6 magnitude, say minus 12, oh, sorry, minus 12, the 12th magnitude, then it will be increased to by 15 magnitudes, it will be a minus 3, right? I don't know. Okay. So, and statistically, from observations, we know that about from 3 to 5 classical novae are actually observed per year. Okay. This doesn't mean that in our Milky Way galaxy, 3 to 5 novae explode per year, because many novae belong to population 1, too young stellar population of the Milky Way galaxy. So therefore, they are located in the galactic plane where there is a lot of dust, and therefore they are obscured by the dust. So many novae that explode in the Milky Way galaxy every year, they are just not seen. So therefore, statistics allow to estimate that given that we really observe from 3 to 5 nova per year, this means that approximately from 30 to 50 novae are actually exploding in the galaxy every year. Okay. So now about observables. We can and did observe from nova explosions optical radiation, ultraviolet, and X-ray radiation in the form of light curves. Light curves just means, say, the flux in the corresponding band as a function of time. That's what light curve means. These light curves actually result from deepening nova photosphere. Remember, when the nova envelope expands, it gets transparent for radiation, and therefore, as it's expanding, we can see deeper and deeper layers inside the expanding envelope. And deeper layers, of course, are hotter. Okay, so as the ejected nova envelope expands, and eventually we can see infrared emission from dust forming in the ejector of nova. That was also observed. So this is all was observed. So in principle, we can use stellar spectroscopy methods to determine individual elemental abundances in nova ejector. This can be done using, again, nova optical, ultraviolet, and infrared emission line spectra. That was done, and this link gives a paper in table 2, of which you can find individual elemental abundances determined for a few elements, determined for different classical nova explosions. Okay. So now about possible observables that unfortunately have not been yet really observed. This is, but they are predicted. So theoretically, they are predicted. So they in principle can be observed under certain circumstances. These are gamma ray lines from electron-positron annihilation at 511 keV kiloelectron volt. With adjacent continuum at low energy cutoff at 2030 kiloelectron volt. This is what is predicted, but has not been observed yet. Gamma lines at specific energies shown here. These energies correspond to decaying radioactive nuclei beryllium-7. The first line, 478 kiloelectron volt beryllium-7, its lifetime 77 days, depends on the temperature and density. The second line, 1275 keV, is expected to come from radioactive sodium-22, which is predicted by NOVA models, including our NOVA framework models, in some non-negligible quantities. But then, of course, the question is how far away the observed nova is, because the further it's away, the weaker the flux in this line. So sodium-22 is radioactive with a lifetime 3.75 years, and aluminum-26, this last line. So aluminum-26 gamma line 1.809 megaelectron volt was actually observed in the Milky Way plane, galactic plane, but it's believed to be produced by aluminum-26 made not by novae, but instead by massive stars. So far, none of these gamma lines was measured yet from a nova explosion. Okay, they have not been observed yet. Finally, peculiar abundance ratios of CNO, carbon, nitrogen, oxygen, intermediate mass isotopes, not elements, but isotopes, produced in non-equilibrium beta plus decay, limited CNO, neon, sodium, magnesium, aluminum cycles, and beyond, up to atomic mass 40, right? So this peculiar isotopic abundance ratios that could be assigned to nova explosions have actually been measured in pre-solar grains from meteoritic samples. As you know, of course, in most cases, abundances of isotopes can only be measured so far only in pre-solar grains. Stellar spectroscopy can measure isotopic abundances only for a few elements like magnesium and oxygen. Yeah, okay, so let's go further. These two images show the explosion of nova Cygni, 1992, which was named V1974, taken 7 months apart in 93 and 94. So this is in this is the first image, and this image on the right was taken 7 months afterwards. And you can see, we indeed see the expansion of this nova ejector envelope, which was caused, as I explained to you, by thermonuclear explosion. Okay. In this project that I'm going to talk about today, I'm going to focus on hydrogen burning nucleosynthesis in one-dimensional hydrostatic nova models. I emphasize that I'm going to use 1D hydrostatic nova models calculated using the stellar evolution code MESA, because in the world there are 2-dimensional and 3-dimensional and codes, hydrodynamic, not hydrostatic computer codes that allow to calculate nova explosions, but they are very limited in terms of the time scale and the resolution. So therefore, so far, many researchers, not only we, use 1D hydrostatic nova models, which allow to do some interesting research in the physics of novae stars. So in this project, I'm going to talk about how to calculate hydrogen burning nucleosynthesis in 1D hydrostatic nova models, rather than to talk about nova photometry or spectroscopy at different color bands or wavelengths. This is an absolutely different story. I'm not an expert in this field, in the field of stellar photometry and spectroscopy, of course. Okay, so this is a summary of what's happening during nova explosion. So this can be considered as a definition of a nova explosion. So the hydrogen-rich material accreted by the white dwarf is being compressed by the gravitational force, and as a result of this compression, it's getting heated up until hydrogen is ignited leading to a thermonuclear explosion. A large amount of heat released by this runaway hydrogen burning at the base of the accreted envelope triggers convection in the envelope and causes its expansion. It is interesting that a similar sequence of events, yeah, now it's a funny thing. Okay, let's focus on this. Again, it is interesting that a similar sequence of events that we see during nova explosion, namely air intake, which corresponds to accretion of hydrogen-rich material by the white dwarf air intake. It's a compression of this air, fuel injection, and combustion, explosion, finally followed by exhaust of burning products. A similar sequence of events takes place in a 4-stroke diesel engine. I will show you in the next slides the corresponding animated picture. The similarity between the nova and diesel engine duty cycles is also enhanced by the fact that a successful nova explosion also needs an injection or mixing of carbon-oxygen or oxygen-neon rich material from an underlying carbon-oxygen or oxygen-neon white dwarf that serves as a catalyst for hydrogen burning in the CNO cycle. So this is an important statement. It was shown yet in 1970s, then in order theoretically to reproduce the observed nova explosion, right? It is not sufficient to assume that white dwarf has just accreted hydrogen-rich material from its companion, and that hydrogen material was ignited, exploded, and started to expand and was ejected eventually. To get a sufficiently strong explosion, as observations show, as the sentence states, we need to assume that either before a nova explosion or during nova explosion. Now, I think most people, including myself, think this happens actually during nova explosion when convection develops in the accreted envelope. Okay, so during the explosion, convection mixes some fraction of material from the underlying white dwarf. So below the hydrogen-rich envelope accreted by the white dwarf, there is a white dwarf. This can be either carbon-oxygen white dwarf for lower initial masses or oxygen-neon white dwarf for high initial masses. And let me just repeat that for efficient, as is observed, nova explosion, the accreted hydrogen-rich material during the explosion has to be mixed with not negligible fraction of material from the underlying white dwarf. Okay, I will talk about this soon. Now I'm going to show you this animation of a 4-stroke diesel engine to illustrate you what I've just said, that diesel engine, 4-stroke diesel engine duty cycle reminds very closely what's happening in classical nova, right? Okay, so this is I call a mechanical analog of novae, which is a 4-stroke diesel engine. Okay, so there are 4 stages during duty cycle of this engine. First, we have here blue air intake, right? Air intake. Then this air here is compressed. Then there is fuel injection and combustion of fuel, and finally exhaust. And all these 4 stages are observed in nova. We have air intake corresponds to accretion by white dwarf for hydrogen-rich material. Press compression corresponds to gravitational compression of the accreted material. Fuel injection and combustion corresponds to mixing of white dwarf material into the accreted hydrogen-rich material during the explosion, during the combustion. And finally, we have the exhaust, which is just ejector, nova ejector. So you can see that this is a very good mechanical analog. This of course, also a joke of novae. Okay. So now here you will be able to see a movie of results obtained with the MESA code, with the MESA stellar evolution code, for the model of nova-like events on a carbon-oxygen white dwarf with a helium buffer layer that accretes hydrogen-rich material. So the only difference of this simulation, MESA simulation, from NOVA simulations that can be done with NOVA framework, I will show you this later. The only difference here is that here white dwarf still has a helium buffer layer. You can see here on this panel, the intermediate right panel, the middle right panel here. It shows decimal logarithms of mass fractions of different isotopes. Okay, it's a mess, but now just for my points about the helium buffer layer, have a look at this top yellow curve. This one, top yellow curve. It shows actually helium-4 abundance. Okay, okay. So now here, and of course along the horizontal line we have just a mass fraction expressed via a logarithm of 1 minus q, where q is a fraction of total mass. We need here to use this fancy mass coordinate, decimal logarithm of 1 minus q, because the mass of the accreted nova envelope here is very small compared to solar masses. You can see, for instance, here the accreted masses for the 10 to the minus 4, 10 to the minus 4, 10 to the minus 5 solar masses. And this corresponds to observational data for novae. So the accreted masses 10 to the minus 4, 10 to the minus 5. So therefore, everything what is here below this vertical line, this is the underlying white dwarf, because you can see here at smaller, at higher masses, we are inside a white dwarf, because here we don't have hydrogen blue anymore. We don't have even helium yellow here. We have here carbon 12 and oxygen 16. So this is the interior of the carbon oxygen white dwarf. But as I said, the difference with the real novae is that here, top of carbon oxygen white dwarf, we have helium buffer layer, which is shown here with yellow. So this is helium buffer layer. So therefore, and only above this helium buffer layer, we have this blue line, which is hydrogen, accreted hydrogen. So hydrogen gets accreted above the carbon oxygen white dwarf, surrounded by a helium buffer layer. So the presence of helium buffer layer makes a hydrogen explosion less violent than in real novae. So therefore, it's easier than to simulate these events many times, these repeating events many times. So now I will turn on this movie and let me show. On the left top panel, this is just a fragment of Hertzsprung-Russell diagram, effective temperature, luminosity. The red dot is the position of the white dwarf of the nova, of this star, before, during explosion, during expansion, and afterwards. So these blue lines, this is stellar evolution tracks that follow the evolution of the star. Ignore this plot, it's not important, it's just central density temperature, it's not relevant. Here you will see how during the evolution, this abundance mass fraction profiles will be changing. So here I show temperature, density, energy, nuclear energy generation rate, they also will be changing. So therefore, yeah, and this is temperature gradients, this anomalous temperature gradients logarithmic with respect to pressure. So I would like, I think I would advise you to have a look only on two panels. Hertzsprung-Russell diagram here, and this in the middle on the right, how mass abundance profiles will be changing. Okay. Now you see this is accretion of hydrogen, now explosion. Okay. You see how explosion changes the evolution of the star. Okay. This is convective envelope shown here with blue. So now the envelope was ejected, and the star returns to low luminosity where it begins again accretion. Accretion, compression, like in the diesel engine, causes expansion, then exhaust, mass loss, via superalkyl luminosity, for instance, or via the interaction with the companion in the closed binary system. And you can see this evolution here repeats many times, okay? Yeah, you can continue to watch this movie at home because it's in the slides. There is a link here, and I will continue this discussion. So almost done with these slides. Let me just summarize the main properties of nova explosion. So the strength of a nova explosion. The strength, by strength here, I mean the maximum, the peak temperature that is reached during the explosion at the bottom of the accreted envelope, right? Of course, the maximum temperature is reached at the bottom of the envelope where the density and pressure have maximum values. So this, yeah, and also as a result, the velocity of expansion. So therefore, the strength of a nova explosion, here in parentheses, I explained this, the maximum temperature of hydrogen burning and the envelope expansion speed. So the strength is amplified with what can amplify the strength of nova explosion? First, the strength is amplified if we increase the white dwarf mass, right? You know that white dwarf masses cannot exceed 1.38 solar masses, which is the Chandrasekhar mass limit. If the mass of the white dwarf exceeds this, we will have, instead of nova explosion, supernova type 1 explosion, right? Which is also observed in the Milky Way galaxy and elsewhere. So a white dwarf with a higher mass has a smaller radius. So mass radius relationship for white dwarfs is such that white dwarf with a higher mass has a smaller radius. Hence, it has a deeper gravitational potential well, right? Mass divided by radius. Therefore, the accreted material is stronger compressed in the white dwarfs with higher masses. This also, by the way, reduces the total accreted mass before the nova explosion is triggered. Because in this case, nova explosions in the binary system occur more frequently. And they are known as recurrent novae in some cases. So therefore, recurrent novae which occur, so normal novae occur once per a few thousand years, okay? But recurrent novae can occur once per tens of years. And in principle, some of recurrent novae can occur on white dwarfs with mass approaching the Chandrasekhar mass limit. So the second thing that can increase the strength of nova explosion is a decrease of the white dwarf central temperature or luminosity. This slows down the heating up of the compressed accreted material. So therefore, as a result, this results in a high accreted mass. And therefore, explosion will be stronger because the total accreted mass is higher if the white dwarf has a smaller central temperature. It's a colder white dwarf. So colder white dwarfs will experience stronger nova explosions. Third factor that can increase the strength of nova explosion is a decrease of the mass accretion rate, okay? So the typical mass accretion rate for novae in closed binary systems, this gives the rate with which mass is accreted by the white dwarf. So the typical mass accretion rates for novae are around 10 to the minus 10 solar masses per year. But if we decrease the mass accretion rates, for instance, if we take 10 to the minus 11 solar masses per year, this reduces the gravithermal energy release rate, which also leads to a high accreted mass. So if the accretion rate is high, then there is a lot of entropy, gravithermal energy with the accreted material. Therefore, explosion of nova occurs earlier, before significant mass is accreted, and therefore the strength for higher accretion rates is weaker. For low accretion rates, the strength of nova explosion is stronger. And finally, the fourth factor that can increase the strength of nova explosion is an enrichment of the accreted envelope, hydrogen-rich envelope, in carbon and oxygen. I already mentioned that this is most likely, this material is most likely dredged up or mixed from the underlying white dwarf by convective boundary mixing, the Kelvin-Helmholtz stability. Okay. That is also needed to erase the helium buffer layer from the surface of a newborn white dwarf. In the previous movie, I showed you instead of a real nova model, nova-like model with a helium buffer layer. Actually, when a white dwarf is just born, as a result of the mass loss by an AGB star. So a white dwarf is just the core of an AGB star that has lost its hydrogen-rich envelope. So white dwarfs are born with helium buffer layers at top. And in order to have, in a closed binary system, realistic nova explosions, this helium buffer layer should be erased. Otherwise, the accreted hydrogen-rich material cannot dredge up carbon and oxygen-rich material from the underlying carbon-oxygen white dwarf to make nova explosion strong enough. Okay. Okay. Here there is a link. I'm going to click on it. A link to the movie from this paper, in which they modeled such a mixing or dredge up of carbon-oxygen-rich material from the underlying white dwarf into the hydrogen-rich envelope by convection, by convective mixing via the Kelvin-Helmholtz stability, as I explained it. So I'm going to click here and start this movie. Okay. So you can see this is a box simulation. So this is just a fragment of a region near the interface between this is hydrogen-rich envelope after the explosion, during the explosion, sorry. You can see there is convection here already, driven by hydrogen burning at the bottom. And convection at the interface between hydrogen envelope and this is carbon-oxygen rich white dwarf. Convection at the boundary results the horizontal motion, shear motion, leads to Kelvin-Helmholtz stability, which dredges up. You can see this dark red material. This is carbon-rich material from the underlying white dwarfs, dredged up by convection and mixed into the hydrogen convective envelope. So this is this is the simulations. Okay. Okay. So now let me go here. Okay. Sorry. Yeah. So, and this is table 2 from the paper that I mentioned before. On one of the previous slides, I provided a link to the paper where you can find this table 2. And it shows, as you can see, mass fractions in nova ejecta from optical and ultraviolet spectroscopy. Of course, this list gives different novae. When you see here the same novae, this means just different reference. So these abundances, mass fractions were determined by different researchers for the same novae. But there are quite a few different novae in this list, in the first column. This is the year of explosion, observed explosion. This is the reference. References are given here at the bottom of the table. And these are elemental abundances that were actually measured in this nova injector. You can see there is, as expected, quite a lot of hydrogen mass fraction, right? Which reach the solar mass fraction of 0.70. This is solar, sorry. For instance, here it's 0.68, like close to solar. There is helium, of course. There is carbon. nitrogen, oxygen, neon, sodium, from sodium to iron. But what's important, please pay attention to this column which has the name Z. As you remember from the slides on the introduction to stellar physics, Z is the total mass fraction of heavy elements, of elements heavier than hydrogen and helium, right? Z. And you can see that in many novae, the mass fraction of heavy elements, it can reach even 0.8, 0.6, 0.4, or 0.35, right? Which means that in the nova ejecta, it can be, as observed, up to 50%, up to 50% are heavy elements. Okay. The question, where these heavy elements come from? They cannot be synthesized during the hydrogen burning. Okay. Hydrogen burning mainly occurs between hydrogen, carbon, nitrogen, oxygen, and the produced abundances of heavy elements during hydrogen burning are negligible. Okay, they cannot be this high, up to 50%. So this means that these high abundances are actually an evidence that during nova explosion, or some researchers say before, but I believe during nova explosion, like I showed in the previous movie, material from the underlying white dwarf, which is made of carbon and oxygen, was just mixed into the hydrogen-rich envelope, was dredged up. And these figures show that up to 50% in mass of the accreted envelope was dredged up from the white dwarf. So therefore, when we model nova explosion in the accreted envelope, we can assume that the envelope has 50% of material from the underlying white dwarf. This is what we'll do in our models. Okay. So the last three slides just summarized main nuclear reactions chains that can take during nova explosion. I already mentioned them. This is CNO cycle reactions here. So I will go fast through the slides. Neon sodium, magnesium aluminum cycles, right? And then some novae that can reach high temperatures. Some novae are believed, and the models confirm that, can reach temperatures close to 450 million Kelvin. In this case, nucleosynthesis can go from CNO cycle up to the production of calcium isotopes. But we believe that calcium is the end point of any nova nucleosynthesis, so up to calcium. Okay, that's it. Okay, so that's it with the slides. Now I switch to, if you don't have questions about the slides, I will go to computational tools. Do you have any questions about the slides? If you have, unmute yourself and ask the question. Okay, it seems there are no questions about the slides. You can have a look at the slides at home. So now let's go to computational tools that can be used, CaNPAN computational tools that can be used to model the nova evolution and the nova multi-zone nucleosynthesis. Okay. So as you already know, to do computation, multi-zone computations of nucleosynthesis, we need to use multi-zone new-grid code, NPPNP. So this can be done only by new-grid members here. So therefore, only you, or those of you who have access to new-grid Wendy can actually do a multi-zone nova nucleosynthesis. But as I explained to you before, in principle, it's not a big deal to become a new-grid member. I'm not going to repeat how to do this. And one more thing. So for multi-zone nucleosynthesis simulations for stars, we need to do two things. The first thing, of course, we need to get, say, temperature, density, and diffusion coefficient profiles as a function of time for our stellar model. For this, we need to use the stellar evolution code. In CaNPAN tools, we use for this MESA, and I encourage you to use MESA stellar evolution code. So NOVA framework, therefore, includes both NOVA simulations with MESA, and then followed by post-processing multi-zone nucleosynthesis simulations with nucleate multi-zone code. And although multi-zone nucleate code can only be used at nucleate Wendy here for nucleate by nucleate members, the NOVA framework MESA stellar evolution code can be used in both AstroHub gateways, in nucleate Wendy and in public and outreach. And you, even if you are not a nucleate member, you can still access public and outreach. So therefore, you can run MESA NOVA evolution computations with quite a lot of nucleosynthesis that is accompanied with interesting nucleosynthesis using this gateway. So I'm not going right now to go to public and outreach. Instead, I will go to nucleate Wendy here. And so I already prepared it here. So this is Wendy 2 server. This is nucleate Wendy. Okay. And here on the left in the file manager, you can see the content of CaNPAN projects repository, right? Yeah. So now let's go to this directory, NOVA. Okay. So here you can see there are subdirectories: NOVA framework, run NOVA CaNPAN, PPN NOVA CaNPAN. So NOVA framework CaNPAN, this is what you should use if you wanna do NOVA evolution computations with the MESA stellar evolution code, right? So NOVA framework, this is NOVA evolution computations with MESA. Run NOVA CaNPAN, this is post-processing multi-zone NOVA nucleosynthesis computations with nucleate code and PPNP. Okay, and PPN, this is one-zone computations of NOVA nucleosynthesis. This can be done even in TINA. I will show you this later. So now I'm going to go to NOVA framework and to show you how to use MESA to model the evolution of NOVA here. Okay, here you can see there are a few subdirectories. See carbon oxygen white dwarf models, neon white dwarf models. There you can see in principle what parameters you can use for NOVA calculations. Okay, for instance, if I click here, you can see neon white dwarf with mass 1.15 or mass 1.3. Okay, the next parameter is the white dwarf temperature, central temperature in million Kelvin. Okay, etc. So I'm not going right now to explain you in detail how to run the simulations. I'm going just to demonstrate to you how to do this because these details are explained actually in README files in CaNPAN project directories. So first of all, there is a main README file, which is in the parent directory, okay? And from this README file, you can read this part, which explains how to run MESA and nucleate codes on nucleate Wendy hub server, okay? And then you go to NOVA subdirectory of the repository. Then there is the README file that explains all details, how to run both NOVA stellar evolution computations with MESA, followed by multi-zone post-processing computations. So therefore, I'm not going to read all these details right now. You can read this later and ask me questions if you will have any. So now I'm just going to illustrate you what in principle can be done, right? So I'm going to close this one. So now, as you can see, I'm in CaNPAN projects, NOVA, Nova framework CaNPAN, a near Nova subdirectory, okay? Okay. So there are two subdirectories in the Nova framework, near Nova and CO Nova. Near Nova, of course, allows you to do mesostellar evolution computations of oxygen near Nova, CO Nova for carbon oxygen Nova, okay? These directories, yeah, and again, details are explained here. So first, please read this README files if you want to use this, okay? So when you're in a Mesa run directory, like near Nova, the first thing you will have to do, and this is explained in the main README file, when you are in a here in a Mesa work directory, run directory, the first thing you have to do, execute these two commands, okay? This one. This first command just tells operational system that you are going to use the Mesa stellar evolution code revision 5329. This is a revision for which we developed this Nova framework. It may not, no, it's not may not. It will not work with our other revisions. So then you execute the second command like this. And this command just tells operational system to use 4 CPUs of the 16th available to run Mesa evolution. LS CPU. You can see LS CPU gives information about this the server. The server has CPUs, 16 CPUs. So you will be going to use 4 CPUs. 4 CPUs is sufficient. Please remember that besides you, some other students can also run codes here. So please don't use here too many CPUs. 4 CPUs are okay. Okay. Now, to start Nova Mesa simulations, you use, yeah, it's explained actually here as an example. This one, you will read this later. I'm not going to discuss this. So there is in this directory a shell script which is called run Mesa. This is where it is, run Mesa. And now I ask the operational system to run this script in the current directory with the following parameters for neon Nova simulations. Take neon oxygen neon wide warp with mass 1.3 solar masses, with the central temperature of 30 million Kelvin. Use for the mass loss rate the number which is named X, and run these simulations for 2010 time steps. So produce 2010 models as a function of time, right? Okay. If for instance I will use for the mass loss rate the letter which is not available, the script will explain you which letters for the mass loss rate are available. You have chosen the oxygen neon wide warp model with the mass 1.3 and initial central temperature 30 megakelvin. The mass accretion rate has been specified incorrectly. Yeah, intentionally I did this. It must be coded by one of the following letters. A corresponds to mass loss rate 10 to the minus 10. I will be using X, which corresponds 2 times 10 to the minus 10 solar masses ending. Okay, so now again I'm going to use X for 2 times 10 to the minus 10 solar masses per year. Okay, now the first question it asks you, it asks, would you like Mesa to take into account convective boundary mixing at the bottom of the accreted envelope that will penetrate into the wide dwarf core? Yes or no? So there are 2 mixing options in our Nova framework, which are explained here. They are explained here. Okay, different mixing options. Okay, so somewhere here. Okay, I don't remember exactly where, but explained here. So the first mixing options will simulate convective overshooting in MESA. The MESA code has such an option. While the second option will just add up initially to the accreted hydrogen-rich envelope 50% of material from the underlying white wolf. Okay, and that's what I'm going to do right now. So I'm not going to use this option, which will model convective boundary mixing. So therefore, I'm going to say no. Then it says MESA will not take into account convective boundary mixing as an alternative, and this is the second mixing option. Would you like MESA to use a mixture of equal amounts, 50-50, of the oxygen neon white wolf and solar composition materials in the accreted envelope? Yes or no? I'm going to say yes, because I showed you table 2, which shows that nova ejecta do have, on average around 50% of white dwarf material in it. So therefore, I'm going to say yes. Then it says MESA, will use a mixture of equal amounts of the oxygen neon white dwarf and solar composition materials in the accreted envelope. Would you like MESA to save the results in a separate directory so that you could use them later? So you can say yes, but now I'm going to say no, because I already have these results in a separate directory, and I don't want they to be erased, right? I will now say no, so that my previously obtained results will not be erased, and I will show you these results, because otherwise they will be erased, and we will have to wait for quite a long time until these calculations will end. And these calculations, MESA nova evolution, calculation, takes about a few hours, maybe 2-3 hours. So therefore, we are not going to wait this long. So therefore, I'm saying no, please don't save them in a separate directory. I already have saved them before. Finally, it says, would you like to start nova simulation with these parameters? Yes, let's start. So now it takes some time for the MESA code to start. Okay, it's relatively slow. While it's starting, I will show you the next thing. Okay, so right now here on the right, it started. It's almost started. Right now I'm in this directory, neon nova, where you can do oxygen neon nova stellar evolution simulations with MESA. Otherwise, you can do carbon oxygen nova evolution simulations. But here there is also a directory with nova notebooks, which allow you to analyze results of your computations, both obtained with MESA stellar evolution as well as with new grid multi-zone code. So therefore, if I go there, there are 2 notebooks here, which I already here turned on. Okay, so therefore I'm going to show you, this is the Nova MESA notebook, which of course analyzes the results of Nova MESA stellar evolution computations, and Nova MPPNP notebook, which analyzes the results of multi-zone new grid post-processing nucleosynthesis computations. So if I go to Nova MESA, Nova MESA, and close this file manager. So it's relatively, unfortunately, it's relatively slow. So therefore, it might take a few hours, but I will show you later how it will proceed. Now I go to Nova MESA. Okay, and now I'm going to clean. Sorry. To clean this notebook. Okay, now I'm going to execute the cells. So this notebook, Nova MESA, plots and analyzes results of carbon-oxygen or oxygen-near-nova MESA stellar evolution computations. Okay. Yeah. Also, always please read comments at the beginning of each cell, which explain what each cell, is doing. So now you can see here the stellar evolution nova computations actually have started, right? And they go on. This is the first model. This is the second model. First, it just provided the list of nuclear reactions that are included in these computations. And as you can see, 442 nuclear reactions are included. So this MESA nova evolution computations can be used without even doing nuclear multi-zone post-processing. We use these calculations exactly, for instance, to write and publish a paper in monthly notes letters about production of beryllium-7 in nova. You can have a look at this paper. So therefore, you can see now it started. Okay. Also, at the beginning of start, you can see here it says initializing SE output, starting a new SE output file for model, this one. So SE output, this is exactly output files for following multi-zone nuclear post-processing. So these files contain detailed information about structure of each of these models, model 1, 2, 3, etc., of each of these models. They give distribution of temperature, density, and mixing diffusion coefficient as a function of radius or mass coordinate, right? So therefore, Okay, so now it started. So now I go to the notebook that analyzes nova MESA evolutionary computations. Okay, let's execute these cells. Okay, so this cell just reads some astronomical and physical constant. Now in this cell, you choose the name of your directory. My directory has name Pavel Den. And then you choose nova case, either CeoNova or NeoNova. Now I have computations for NeoNova. Okay, this directory. Okay. So now, while you are running nova MESA evolutionary computations like here, right? The results of these calculations are saved in a standard MESA directory logs and photos. Okay, so therefore this notebook can be used while your nova evolution computations are still running, okay, in the process of running. In this case, you choose just logs directory. This is the default MESA directory. And let's see what so far the code has achieved. Not much, only 22 models have been calculated, as you can see, but let's check. Yeah, 20 models. Yeah, so this is Hertzsprung-Russell diagram of our current calculations. And you can see we have not reached much. We have started with this, but luminosity already increases, is increasing, as you can see, okay? So, but otherwise there is nothing interesting here. So therefore, I'm going to switch here to change the name of the directory here from MESA default, where so far there is no much, only 26 models. I'm going to switch it to my previously saved directory for the same computations. As you can see, this is what's happening when you say yes to the script to save results at the end. They was saved here in directory logs underscore 1.3. Oxygen in White-Wolf mass, 30 megakelvin central temperature, X mass accretion rate 2 times 10 to the minus 10 solar mass per year, 2010 models. Mixed here means I assumed that the accreted material was pre-mixed. It has 50% solar composition and 50% underlying White-Wolf. So I'm going to pick up these results so that we make can make meaningful plots. Now you can see there are a lot of models to 2010. Okay. And now you can see this is what you will obtain this result at the end of these calculations, which will take, I would say, a couple of hours. Yeah, but of course you can take coffee, have a lunch. Yeah, everything will be running on this server. So you can see this blue line shows the stellar evolution track of this nova computations. It started here. This is when actually explosion has started. Then as a result of the explosion, luminosity increased, as you can see, from 1/10 of the solar to above 10,000, as it should be for novae. And then the stellar evolution track, it returned back toward the asymptotic giant branch, right? Because at this moment, the star, white dwarf with expanding envelope, does look like a red giant, becoming to look as a red giant, okay? And this diagonal line, orange dashed, it actually shows the Roche lobe radius for the white dwarf here, for the mass ratio of the white dwarf to the secondary star 0.52, and for period 2 hours. So this means at this moment, the stellar evolution track crosses this line, which means at this moment, the radius of expanded envelope exceeds the Roche lobe radius, and we expect that this material will be lost from the binary system, okay? So the envelope will be lost. Now let's go to other cells, excuse me. Some of them take time to execute, and the comments usually warn about this. So it says this cell may take a few minutes to execute. Let's check. Yeah, so far we have 52 models calculated. Okay, so I'm going to stop this calculation so they don't slow down our work with the notebook, right? You've got the idea. I'm going to Control-C, I just stopped these calculations, okay? I'm still in this directory. Otherwise, calculations actually take processing time, and they can slow down our execution of the notebook. Yeah, you can have a look at these notebooks at home later. As I said, this notebook, as well as Mesanova calculations, can be run on the AstroHub public and outreach that can be accessed not by any one of you, right? Okay. So now we are going to plot temperature profiles, right? These are temperature profiles. So decimal algorithm of temperature in the envelope as a function of this funny mass coordinate. Again, we have to choose transform a mass coordinate. So because the mass of the critical envelope is small, it's of order 10⁻⁵ solar masses. But otherwise, so this vertical line corresponds to the interface between the white dwarf to the left and the critical envelope to the right. And these curves show, as you can see, for different models calculated with these numbers, time steps, they show temperature profile. You can see that the maximum temperature, of course, is reached at the bottom of the accreted envelope here. And its peak value reaches almost 300 million Kelvin for this NOVA model. Okay. Okay, so this is a useful plot. This is a 4-panel plot, which summarizes several NOVA model properties. The top left is again Hertzsprung-Russell diagram. The top right temperature profiles that I already showed you. The bottom right is the density profiles, and the left bottom here is the mass fraction of helium-3. Okay, you can change what's plotted here. So this is a summary. Okay, etc. So everything should work. Everything works. You can have a look at this plot. So the next step, after we finished our MESA nova stellar evolution computations, and as a result, you can see this directory was created. Okay, so this directory contains those SE files. They have a special format, it's HDF5 files. They are compressed, but these files can be used as input data for multi-zone post-processing nova nucleosynthesis computations. Okay, so for this we need to use the code which is here in run nova CaNPAN. Okay, and this is explained in detail in this README file. So I'm not going to repeat this. Just you can read this, and if you will have any questions, just ask me. So what I'm going to show you next, the analysis of results obtained with multi-zone new grid code for the same nova, model, oxygen nova with mass 1.3. etc. For this, I use the second notebook from Nova Notebooks, Nova MPPNP, right? Okay. So plot and analyze results of CO oxygen Nova MPPNP post-processing computations, including plots for the chlorine 34 project. So some cells here take several minutes to execute. Therefore, I've executed them before our meeting today. I'm going just to walk you through these cells. Okay. Again, here choose the name of your directory. Okay, and the name of the nova case, either CO or near nova. Okay. This cell reads output data produced by multi-zone new grid code. Okay. Then other cells make plots like mass fraction of various isotopes as a function of this fancy mass coordinate. But these are results already from multi-zone new grid post-processing, not from MESA stellar evolution simulations. Of course, they can be compared. Usually they agree pretty well. Now, beryllium-7, this is plot was used for our beryllium-7 paper. You can have a look at the paper. And I show you that all the results obtained in this beryllium-7 paper, in multi-node letters, were obtained with this nova framework using only MESA part, without doing multi-zone nucleosynthesis simulations. This is helium-3 abundance. Okay, this is chlorine isomers abundances. Okay, this is from another paper. From multi-zone simulations, here we extract peak temperature and peak density as function of time. This can be used as trajectories for one zone, for the corresponding one zone nova simulations, and then we can compare results of nucleosynthesis simulations from one zone and multi-zone. This is done in this notebook as well. So this is where this trajectory is written in a trajectory file. Okay. This is how the mass of the critical envelope was increasing with model number, which is called here cycle. It's just time step model number. And now here we plot mass fractions in the nova envelope, and yeah, so here below you can compare results of nucleosynthesis simulations done with one zone nova and multi-zone. for one zone, of course, you are supposed to use this trajectory for comparison, the same trajectory that was extracted from the corresponding multi-zone simulations, right? Okay, so therefore, in order to execute the following here, the next cells, you have to first decide to tell the notebook, have you already done one-zone post-processing simulations for this NOVA model? Here I say no, false, they have not been done yet, although I think they have been done actually here. And then we have, so these are mass fractions with respect to the corresponding solar values in the NOVA envelope as a function of a mass number. And for instance, you can compare this with this plot with the corresponding plot in publications by Barcelona group, Jorge Jose and Margarita Fernandez. They have very similar plots, so therefore our results are consistent with results actually obtained by other groups, by Barcelona group and by Zamner-Starfeld group in the US. Okay. Okay, so that's it for this package, NOVA framework, NOVA mesostellar evolution simulations followed by new grid simulations. Again, if you're interested, read the details in the README files. And now there are 10 minutes, almost 10 minutes left. Let me also show you how you can run one-zone NOVA simulations in TINA. So for this, I go to TINA here, okay? And this is your TINA network school directory. This is mine, Pavel. Network school, Pavel. You should have the similar one. So here you go to NOVA, okay, subdirectory. And again, like in other TINA subdirectories, there are the same notebooks with the same names, Model Runner and Result Explorer, okay? So you go to Model Runner, okay, Model Runner. And for NOVA case, for NOVA project Model Runner, for NOVA, you can see there are 8 cases for one-zone NOVA simulations. So here it is explained to which set of NOVA parameters each case corresponds. The first number is the white dwarf mass, carbon oxygen neon, white dwarf central temperature, and the latter codes mass accretion rate. Mixed, you know what it means. Barcelona is just the initial chemical composition from Barcelona group, okay, or from Archive. So now I'm going to take case 6, which corresponds to my run that I have just done in NOVA framework, right? Case number 6. So therefore I say run NOVA case 6 here. And this is TINA, so you can try this. There are no limitations for you to try this. So look at this. So you see, this is just one-zone NOVA simulations. You can see this is temperature taken from NOVA trajectory. Temperature increases from 100 million. This is density from 10,000 goes down. Density temperature increases from 100 million to 350 million, 360, yeah, maximum 360, while density decreases because envelope expands, right? Starting from 10,000, going to 100, etc. Okay? So one-zone simulations, of course, are pretty fast, as you can see. And that's it. Now, of course, don't forget to save your results. I will save them in directory with name case_6, of course. Okay, like this. They are saved. Now I go to Result Explorer notebook. Result Explorer notebook for NOVA project. Okay, they're different for different projects. Okay, now let's execute the cells. Here you have to provide the name of the directory where you saved the results of your computations. So they're red here. Then let's make some plots. This is the plot of abundances, chart of abundances. So, excuse me, you can see in this case, nucleosynthesis ANOVA proceeds up to calcium because temperature is high, 360 million, up to calcium. There is a lot of elements produced in chlorine isotopes, argon, sulfur, phosphorus, silicon, etc. Okay. Now here we did temperature density from the trajectory that we used in this one-to-one simulations, just to make its plot. So this plot shows what temperature, the orange, and what density as a function of times we used in these computations. Okay, so this is a useful cell as well. Here you can see I'm going to compare the rate for the reaction nitrogen-13 P gamma that was used in these calculations with some other source for the same rate. To do this, first of all, before I start one-zone NOVA calculations, okay, using model runner, I open ppn frame.input file, ppn frame input, which specifies input parameters for one-zone calculations. It's open here. Okay, and at the bottom of the parameter list here, you can specify the number of reaction you are interested in to check in the file network setup.txt. Okay, so this file, this one here, it's open here. This is file network setup.txt, which just gives the full list of reactions used in one-zone computations. Okay. Sorry. Yeah. And if I'm interested in the reaction, okay, if I'm interested in the reaction nitrogen-13, oh, what reaction I'm interested in? Nitrogen-13 P gamma, right? I check where it is. This is nitrogen-13 P gamma, right? And you should check that there is a letter T in the second column. T means true. This means it is this rate that was used in calculations. If instead of T there is F, false, which means this rate was not used, and you should look at this list further down to find the same reaction where instead of F there will be T. But nitrogen-13 P gamma, here we have true, so that is number 16. So therefore in pp frame I say I want to make a plot for the reaction with number 16, and I have to provide electric charges for the first for the nuclei in the input channel. This is nitrogen-13. Nitrogen has charge 7. Proton P gamma has charge 1. This has to be done because there is electron screening factor which has to be deleted, which depends on the charges. So after that, in the result, after that I have to rerun my simulations, and then in the result explorer now, by the way, also the name of the files where the rate will be stored, and 13 P gamma rate. So now in the result explorer notebook, I can make the plot of this reaction rate that was used in simulations. In this case, I compare it with the prescription, analytical prescription taken from the same code. So therefore, the rate should be the same. But you can use here for comparison a different prescription for the same rate, right? So then this produces the plot like this. Okay, so it says the red one is the rate that was used in your actual computations, which is red, and the dashed blue is what is taken from NuGrid analytical prescriptions for the same rate. So therefore, it's not surprised that they coincide. On the other hand, if, for instance, I take here, do I still have it here? Yeah, I still have it here. If, for instance, I take here carbon 12p gamma, right? Carbon 12p gamma, and take the rate that is used in the so-called part of the NuGrid program, vital, okay, like this. So you can see that the rate that was used for C12p gamma is slightly different from the NuGrid default rate, because in this case, NuGrid was using actually NACRA rate. This can be checked in this file network_setup.txt. C12p gamma here, C12p gamma, you see it's false. So this means that not vital rate was used. If you go down, you will see this is was actually NACRA. Okay, so therefore some simplistic rate comparison can be done in this notebook as well. Okay, I think that's it so far. So this is all I was going to tell you about NOVA simulations with CaNPAN computational tools. So I'm going to stop sharing my screen. And now you have, if you have questions, please ask your questions. If you have questions, you should unmute yourself and just ask your question. I think you can, yeah, you can do this. You can unmute yourself. If there are no questions, then that's it. Thank you for watching. And I will send you a link to today's video recording as soon as possible. Okay, see you next Friday. Bye-bye.
Bye. Thank you.
Mm-hmm.
Thanks, Pavel.